electrochemistry. Electrochemistry is all about electrons. And at this point, before watching this, make sure you know how to assign oxidation states. Oxidation states are showing if something has gained electrons to become negative or something has lost electrons to become positive. You should also understand at this point that we use this little thing called oil rig. Make sure you understand before watching this that if something is oxidized, it loses electrons, and when something loses electrons, it becomes positive. Reduction is gaining electrons, so if something gains electrons, it's becoming more negative, so something that's reduced becomes more negative. So make sure you understand those two things before watching this. You got that? You're ready. So what we're looking at is, where do the electrons go, and when will they actually move from one thing to another, and how favored will they be? So the way we actually measure how favored something is to move from one place to another, how favored an electron is to move from one thing to another, it's called standard reduction potentials. You have a table of standard reduction potentials in your graded sheet. It's the page that we haven't used, and it says standard reduction potentials. All the standard reduction potentials are measured, they are these E naught values, and the naught means that these reactions were carried out all over the world under standard conditions. So that's my room, 25 degrees Celsius, 1 atmosphere, that's where I'd like to do my lab work. So that's how all these reactions are compared, and then they were placed into a table and we get to use the values that somebody else found for us, which is nice. Standard reduction potentials are a comparison with hydrogen, because here's the problem. Can you have a reduction without oxidizing something? No, because it's redox, reduction, oxidation. To reduce something in the standard reduction potential, something else had to lose an electron. So the entire table on that sheet is comparing with hydrogen. How much more stable does an electron become if I take that electron from hydrogen and I put it on a metal? How unfavored is it if I take an electron from hydrogen and I put it on some non-metal or some metal? So it's comparing everything to hydrogen. And it's just like sea level. So for sea level, we just set sea level at 0, and then elevations all over the world are going to be something compared to what we said sea level was. We could have chosen any height, and then what we can do is we can say, well, I know Death Valley is 200 feet below sea level. I know Queen Anne in Seattle is 400 feet above sea level. So now that I have all these values, let's say that there was another place that's 100 or that's 550 feet above sea level. Well, then I know to go from 550 feet above sea level down to Queen Anne, it's a loss of 100 feet. I know to go from Queen Anne down to Death Valley, that's going to be a loss of 730 feet. So by having sea level, we can compare all elevations versus this. By comparing everything to hydrogen, we can actually get the total standard reduction potential of any reaction. So the way it works is, if I were to take an electron from hydrogen, making it hydrogen ion, and I take that electron and put it into lithium, a lithium ion, I've reduced the lithium, and on my grid sheet it says that is unfavored by 3.05 volts. And in a separate reaction, somebody went ahead and measured for me. If they take an electron from hydrogen and they put it in fluorine gas to make fluoride, they said, well, that one is favored by 2.87 volts. Okay, so these are both measured. I can now calculate the change in stability if I took an electron from a lithium atom and oxidized the lithium down to lithium ion and took that electron all the way down to fluorine. So the electron would become 3.5 volts more stable as it went from the lithium to the hydrogen, it's positive, and it would become 2.87 volts more stable as it went from the hydrogen to the fluorine. So all in all, I would just add 3.05 plus the 2.87 and get 5.92 volts more stable. So by comparing everything to hydrogen, we can actually calculate the standard reduction potential of any reaction. Tricky things. So I kept saying favored. If you have a hard time remembering that positive standard reduction potentials are favored, one thing that I used to do was just look at the top of my sheet and I see that when fluorine gains an electron to become fluoride, that's a positive value. That's the largest positive value. And I know, so that means Either fluorine is the least likely thing to be reduced or the most likely thing to be reduced. I know fluorine's the most electronegative element. It makes sense then that that's the most likely thing to be reduced. So positive values must be favored for standard reduction potentials. Okay, let's go ahead and calculate one real quick. Let's go ahead and see if I'm going to take an electron, real quick, we're just looking at if I were to take an electron from, let's say fluorine. So we'll take our fluoride, because I can't reduce fluorine, I can reduce fluoride, or I can oxidize fluoride. I'm going to take an electron from fluoride to turn it to fluorine. So I've got a negative over this side, I've got two fluorines, got a 2 minus on this side, I'm going to need 2 electrons over there. So that's how I balance this half reaction. I use electrons to balance the charge. And then I can see this is being oxidized. Here fluorine is being reduced. So since I'm doing this the opposite direction of this is what's on my Greg sheet. I'll flip the sign of that. So negative 2.87 volts. I'm going to take those electrons, I'm going to put them on lithium. So I'm going to have lithium ion. So if my fluorine is being oxidized, I'm going to have the lithium be reduced to lithium atom. And then, oops, I can see that I've got a positive on this side. This is neutral. I'm going to need an electron to balance that charge. And the next thing I say is, well, if I released 2 electrons in my oxidation, I have to consume 2 electrons in my reduction. So I'm going to double this whole thing. So 2, 2, and 2. So now when I get my standard reduction potential, lithium, when it's reduced, electrons become more stable or less stable by negative 3.05 volts. I'm not going to double that 3.05 because the electron became 3.05 volts. That's what this is talking about, or less stable by 3.05 volts. How much more stable is the electron? It's not talking about the total stability lost. So it's kind of like if one person travels from Queen Anne down to sea level, they've lost 450 feet of elevation. If 2 people travel, each of those people lose 450 feet of elevation. There isn't a 900-foot change of elevation, it's just that each person lost 450 feet. So all in all, this was unfavored by 5.92 volts. I'm going to show you what we just did in a slower format, showing the steps of this. So this was really just saying if I took the electron from the fluorine and put it to the lithium, how do I use standard reduction potentials to calculate the standard reduction potential of the whole reaction? So the things I just did, I split my reaction into reduction and oxidation. Every redox reaction has a reduction and an oxidation. They both have to happen. So let's do that first. In order to do that, you have to know how to assign oxidation states. This is where we needed that. This magnesium is with 2 chlorides, so it's a 2+. Gold by itself, anything by itself is 0. Here the gold's with 3 chlorides, it's a 3+. And here the magnesium's by itself, so it's a 0. Split this into reduction and oxidation. Well, I know oxidation is the loss of electrons. Something loses negative electrons, it becomes more positive. Gold is the thing being oxidized. So my oxidation is that 2 gold atoms turn into 2 gold ions. Right, so I've got a neutral side over here. This has a 2 times 3, 6+ side. I'm going to have to add 6 electrons to balance that charge. Then for my reduction, well, magnesium gained electrons to become neutral. So I have 3 magnesium ions. They become 3 magnesium atoms. I've got a 6+ here, neutral on this side. I'm going to need 6 electrons. Okay, this was already balanced for me. The 2 half reactions were balanced because I started with a balanced equation. So that's cool. Then what I'm going to do is I'm going to find the potentials on Greg. So magnesium is being reduced, so I just look on my Greg sheet, and when magnesium is reduced, it says Mg2+ plus 2 electrons makes Mg, and the reduction potential is unfavored by 2.37. Okay, so negative 2.37 is what that says. So magnesium ion is better at taking electrons than hydrogen ion. Sounds right. And then, meanwhile, I know gold atoms are pretty stable. I don't have the reduction here, so I look on Greg. And on Greg, I'm going to see this. AU with a 3+ charge gains 3 electrons to become AU. And it says that's favored by 1.5 volts. It's positive. Well, reducing gold is positive, so oxidizing must be negative. So this is going to be a negative 1.5. All right. Even though this has 2 golds, I'm not going to double this because electrons become 1.5 volts more stable when they go from hydrogen to gold, and I'm just going to leave it like that. So now I have, this guy was unfavored, this guy was also unfavored, so this is a reaction that's not going to occur, so I've got 3.87, negative 3.87 volts. Okay, so I just found out that if I'm going to take magnesium chloride and gold, it's not going to react, which is good, so my gold's safe, since it's a negative voltage. Well, look at this one. This one's actually on your homework. I'm going to split into the reduction and the oxidation. So this is a 2+ with the 2 chlorides. This is 0 by itself, 0 by itself, 1+, because it's with 1 chloride. Okay, the thing being oxidized, oxidation is a loss of electrons. It's becoming more positive. Silver. So Ag to become Ag plus is that. And then meanwhile, I have iron. So I've got Fe2+ becomes Fe as a solid. All right, so to balance this, I've got a 1+ on this side. Okay, and I can actually say I've got 2 silvers, making 2 silver ions, so I'm going to need 2 electrons. And I also have iron as a 2+, becoming iron as a solid. So I'm going to need 2 electrons here. I started with a balanced equation, so the electrons were balanced too. So then I look on the grid sheet to find the standard reduction potentials. Iron plus 2 electrons is just written as it is, and Fe2+, I have negative 0.44. So those electrons were more stable in the hydrogen than they were in the iron. Okay. And then for the silver is written backwards because on my Greg sheet, I'm actually going to see this. I'm going to see Ag plus 1 electron makes Ag, and the electron is becoming more stable, because silver is very stable, by 0.8 volts. Okay, so when I flip that to oxidize the silver, it's unfavored by negative 0.8. So I'm showing you reactions that don't happen, just because I randomly chose these. 1.24. So electrons would become 1.24 volts less stable by going from the silver to the iron. So it's good, your silver is safe also. All right, so split your reaction into what was reduced, what was oxidized. Find the potentials on Greg. Make sure you have your half reaction lined up in the same way as it is on Greg. If you have to flip the Greg reaction to match what you have here, flip the sign of the standard reduction potential. Do not multiply potentials by coefficients because you're just saying electrons become more stable by this amount. You're not saying the total energy lost or gained.